We saw in the last video that it's quite difficult to launch a payload into orbit using a single-stage rocket. What if you stacked two rockets together so that the payload for the first stage was the second-stage rocket? Would this make it easier to launch a payload into orbit? Well, the answer to this question is yes, and in this video we're going to investigate why staging rockets is almost essential for using rockets to launch into Earth orbit. This photo shows a two-stage launch vehicle with the first stage firing. In fact, this is the Terrier Orion stack that was used to launch the high-shot payloads. While this was not an orbital launch, it shows you how you stack rockets for multiple stages. The key thing with staged launch vehicles is that the payload for the first stage is the second stage rocket. So here we see the first stage, let's just draw that, the first stage firing, and the second stage is sitting on top of the first stage. And once the first stage burns out, that stage will drop off. The second stage motor will then fire and take us into orbit if this is a two-stage orbital launch vehicle. So here's a sketch of our two-stage launch vehicles showing the first stage below the second stage. Our payload is sitting on top of the second stage, so let's say that that's the mass of our payload. The second stage is also carrying the propellant for stage 2, so let's call that MP2. And then we've got the rest of stage 2 is going to be the mass of the structure of stage 2, so that includes the structure and the engines. So all of this is the payload for stage 2, for stage 1. Stage 1 also has to have its propellant, so we've got the mass of the propellant for stage 1. And then the rest of this is, we're saying, the structure, the mass of the structure for stage 1, so MS1. So the overall mass that we'll have at takeoff we'll call M01, and that's going to be the mass of the payload that we finally want into orbit, plus the mass of the structure for the second stage, the mass of the propellant for the second stage, the mass of the propellant for the first stage, and the mass of the structure for the first stage. So let's call that equation 1. Let's now look at what's the final mass for stage 1. So we'll call that MF1, and that will be the mass of our payload plus the mass of the structure for stage 2 and the mass of the propellant for stage 2, and we're still left with the mass of the structure for stage 1. So the only thing we've got rid of is the propellant from stage 1. So we'll call this equation 2. Now when the first stage has done its job, we're going to throw away what's left of the first stage. So let's throw away the mass of the structure of stage 1, and we'll just let that drop back to the Earth. So let's look at the initial mass for stage 2. We're calling that M02, and that's going to be our payload plus the mass of the structure of stage 2 plus the mass of the propellant for stage 2. So we've got rid of the propellant for stage 1 and now the structure from stage 1. So we'll call this equation 3. Now, comparing equations 2 and 3, we can note that the final payload for stage 1, or the final mass for stage 1, is M02 plus MS1, and we'll call that equation 4. And then the final mass into orbit, which is going to be our MF2, is going to be equal to our payload plus the structure or the structural mass of the second stage. So those are the basic equations that we need. Let's now look at our single stage to orbit example. For that example, we had the effective velocity change we said was 9.7 kilometers per second, and we had a structural to initial mass ratio of 0.07, and we had our payload to initial mass we calculated would have to be 0.02, and we also had our propellant was being ejected at a speed of 4 kilometers per second. Let's now consider a two-stage launcher. So a two-stage rocket. And what we're going to do is let's keep the structural mass fraction the same. So let's say that we can build these rockets with an ms over m naught of 0.07. And we'll apply that for both the first stage and for the second stage rocket. And let's also keep our VP at 4 kilometers per second, and again for each stage. Just slide that window down. Let's also keep our overall delta V effective at 9.7 kilometers per second. So we're looking to launch into low Earth orbit again. But we need to decide how much delta V effective we get out of each stage, and to keep it simple, we'll let each stage of our two-stage launch system do half the delta V effective. What I mean by that is delta V effective is equal to half of 9.7, which is 4.85 kilometers per second for each stage. Therefore, for both our first stage and our second stage of this two-stage rocket, we'll have the rocket equation will give us that the final mass over the initial mass is equal to E to the minus delta V effective over VP. So that's going to apply to each stage, and for each stage we have delta V effective is 4.85 kilometers per second. Our VP we said was 4.0 kilometers per second. So that means that the ratio of the final mass to the initial mass works out to be 0.297. So we'll mark that as equation 6. Just slide that window down a little bit. And let's start off with, let's look at stage 2. This turns out to be the best way to approach this, is consider stage 2 first. And equation 5 is going to give us that the final mass for stage 2 is equal to the mass of the payload plus the mass of the structure of stage 2. So let's write this as mf2 over m02, the final mass for stage 2 over the initial mass for stage 2, is the mass of the payload over the initial mass for stage 2 plus the mass of the structure over the initial mass for stage 2. But for both our stages, the structural mass over the initial mass is 0.07, as we've got up here. So this term here is going to be equal to 0.07. And we also have from equation 6 that mf over m naught is 0.297 for each stage. So this term here is equal to 0.297 from equation 6. So putting that together, we get 0.297 is equal to MPL over M02 plus 0.07, and that gives us that the ratio of the payload mass to the initial mass for stage 2 is going to be equal to 0.227, and we'll call that equation 7. Now let's slide the screen down again, and we'll move on to consider stage 1. Now for stage 1, equation 4 gives us that the final mass for stage 1 is equal to the initial mass for stage 2 plus the structure of stage 1, the mass of the structure of stage 1. So let's write that as mf1 over m01, so we're dividing everything by m01, is m02 over m01 plus ms1 over m01. And again, we can say that the structural mass fraction is 0.07 because we've said it's the same for both stages, and because we're getting the same performance out of each stage, the mf1 over m01 is going to be again 0.297 from our equation 6. So therefore we can write that 0.297 is equal to m02 over m01 plus 0.07, which gives us that m02 over m01 is equal to 0.227, and we'll call that equation 8. Now let's take equation 7 and multiply it by equation 8 to give us that MPL over M02 times M02 over M01 is equal to 0.227 times 0.227, which gives us an overall number of 0.052. So this gives us that the mass of the payload over the initial mass that we've got on the launch pad at takeoff, M01, is equal to 0.052. And we can compare that with what we had for the single stage to orbit. Single stage to orbit, this ratio was only 0.02. So we've more than doubled that ratio by going to the two-stage rocket. So to get the same payload into orbit, we'd need an initial takeoff mass of less than half that needed for the single-stage launch vehicle. I'll summarize this in the next video.